You're doing well, class. Today we're going to be talking about important properties of waves. Now, the one thing I would like for you to do is make sure that you have your notes out and take your notes as I'm going through this. If you need to, you can pause the video and later on you can play it back and write down the information as we go along. And also, there are going to be some questions embedded in this video. And as long as you answer the questions and submit them within the time frame of this class, you'll be counted as being present for this class and also will get credit for this assignment as well. Otherwise, you'll be counted as being absent. So please take your notes, do the questions, submit them within the time frame of the time that we are supposed to be in class here. All right, so let's get started. So we're going to be getting into some of the different properties of waves here. And keep in mind, this applies to just about any type of wave. So whether we're talking about mechanical waves in, for example, earthquakes, it could be light, it could be sound, it could be waves of water. So these are properties that practically all waves will demonstrate in one form or another. So the first one is that waves can be reflected. And when a wave hits a reflecting surface, is reflected outwards at the same angle as it came in. So if you have some sort of surface here, for example, if this is a mirror, there's a term here that I want you to be familiar with. This yellow dotted line here is called the normal. And normal is basically, in math and science, is referred to as being perpendicular. And so this line is perpendicular to the surface. So the incident ray is the incoming ray. In other words, if you're shining a light bulb or laser at a mirror, this is the incoming ray. So they call this the incident ray. When it strikes the surface and bounces off of it, that's your reflected ray. The angle between the incoming ray and the normal is referred to as the angle of incidence. And then the reflected ray, the angle between the reflected ray and the normal line here is also called the angle of reflection. And as you notice here, the angle of incidence is equal to the angle of reflection. In other words, the angle that this comes in will be exactly the same angle as it leaves. Same thing happens if you're bouncing a ball. The angle that a ball hits a surface, it'll bounce off at the same angle perpendicular to that surface. So if it comes in at a more shallow angle, it strikes the surface, it's going to reflect off at a shallow angle. If it comes in at a very steep angle, it's going to reflect off at exactly the same angle on the other side of this normal line. So when it hits, you draw a line that's perpendicular to the surface, and you measure the angle from the normal to the incoming ray and from the normal to the reflected ray. And these two angles are identical to each other. One example of this is, if you just shine a light off of a mirror as it reflects off, if you're dealing with sound, this would also be like an echo. The sound waves coming in, strikes a solid surface, and it bounces off. Now here's another example here where this is actually referred to as internal reflection, but a laser light is shined through what I believe to be an aquarium, and it strikes the surface of the water and is reflected back down into the water again. But again, if you notice, this is the surface right here, and if you imagine the normal line, the angle from here to the normal is the same angle as from the reflected ray to the normal line. And also, if you look at all the individual rays coming off of a scene here, if you have a very flat lake, the image that you see here is nearly identical to what you see up here. So every single wave of light is striking the surface of the water and reflecting off at the same angle. So what we see here is basically the same thing that we see down below. Now another term that kind of sounds similar to reflection is what's called refraction. This is a little bit different. So this is when waves bend when they go from one medium to another. For example, here, if a light ray is going from air into glass or water. Now this time, the ray will bend towards the more optically dense material. So for example, if we're talking about air and glass, the glass is more of an optically more dense material than the air, or the same thing like if you're talking about air and water. The water is more of an optically more dense material than air. Now, again, when the light wave strikes the surface of the water, you draw a line that's perpendicular to the surface. Now, this looks like the adjustments got off a little bit. But what happens here is that they're not equal to each other. So this is air, and say this is maybe water or glass down here. The angle that the light strikes the surface of that, when it passes into the other material, it will pass down so it has a smaller angle. So that this angle of the less optically more dense material will be larger than the angle of the more optically dense material. And the same thing is also true whenever the light passes through the other side. So for example, let's say this is a block of glass. So when the light passes through the other side, it's going from a more optically dense material to a less optically dense material. So it will, the angle of this will again will be larger than the refracted ray. So in this situation here, within the more optically dense material, you're going to have a smaller angle than in comparison to the less optically dense material. And kind of similar to with the last part, where we have theta I, this is a symbol which we typically use for angle, for incident, and this is for reflected. And whereas for this is for incident, and this stands for refracted. And here's another example here where a beam of light passing a piece of glass, and as it bends through here, perpendicular to the surface of it here, it actually bends a little bit more closer towards the normal line, and then when it exits, especially if these two sides are parallel, this line and this line will be parallel to each other. And here's another one where shining a laser into some water, and as you can see here, that if you draw a line straight down through here, the angle between the incident ray and then if you look straight down here and the angle of the refracted ray, this is a smaller angle than what you would see up here. Now, a couple other places where you might see this taking place. If you put a spoon into a glass of water, the way that it looks like the spoon has become detached from the handle. Or if you ever gone standing on a pier looking at the fish in the water, where you see the fish is not where they're actually located. Typically the fish are a little bit closer and a little bit deeper than what you actually are seeing. So for example, like in this image right here, someone who is fish hunting here, spear fishing, if they're up on the surface looking down, they'll see the fish right here, when in actuality the fish is down here. And so if you try to aim for this, you're always going to miss the fish. So you have to kind of learn that the fish is not where you actually see it. And here's another image here where someone is in a pole of some sort, and it looks like their bodies, their head and arm are detached from their body, when in actuality it's because when we're seeing them, they're actually right here, but because of the refraction taking place within the water, it looks like they're being disjointed. It's the same thing that's happening here with the spoon in the water. Now, one other thing that refraction is able to do is if you're looking at white light is a combination of many different wavelengths of light. And when it passes through a prism, it'll separate it into its constituent parts. So different wavelengths bend at different angles, which is what makes a prism separate white light into all of its colors, or what, like Roy G. Biv. So what happens here is that red light is refracted the least. More on the blue end of the spectrum, it bends the most. So more of your blue violets, they're refracted, have a greater angle of refraction, and red light has a lesser angle of refraction. And again, you can see like this part right here, the light's coming in. Now some of the light got reflected off the glass here, but for the rest of the light passing through here, it started breaking it apart into its different primary colors. Now if this was only one color light, this will not happen. So this, with white light is a combination of many different wavelengths of light. And again, the white light coming in, being broken down into its constituent parts. Now refraction is also what makes lenses work. So light bends when it goes from air to glass. So if you have the incoming light coming in through here, it will focus it. There is what's called a focal point where all the rays of light will merge at one central point. Now at this point, then they will begin to diverge after that point. But this is the point where all the incoming light will focus to. And again, this is no different than what's happening with these other images up here. Now you're dealing with a curved surface. And here's a couple other examples here where using a light bulb or a light box and with rays of light, and as you can see here, it's kind of hard to see here through the lens, but all the rays of light will converge here. Or you can have a diverging lens where it will spread the light out in different directions over here. Now diffraction is a little bit different. It is where you have an incoming wave coming into an opening, but then it causes the wave to bend as it passes through the object. And also, if you notice over here, you have no waves over here and also no waves over here. But eventually, these waves, and when they pass through here, will actually begin to spread out and begin to wrap around this barrier. So light bends when it goes around, it should be around obstacles and through openings. And here's a few other images here. So you have water waves passing through a small opening. As you can see here, you end up kind of getting this cone that goes out. Or if you have these waves coming through here and it hits a block, and again, you don't have any waves over here, but if you notice, they eventually will go wrap around the block. After traveling a certain distance here, they eventually will come back together. Now there's also an unusual thing is if you have what's called a monochromatic light, which basically means you have light that only has one wavelength to it. So something like a laser. And when you strike a surface, and especially if it has a sharp surface to it, sometimes you'll end up getting these diffraction rings around it. And so for example, if you shine a light at a penny, you'll start seeing these rings that form around it, and these are diffraction rings. Now there's also one point, and this is in a shadow. The brightest point of a shadow is actually in the center of this. There's one little tiny point of light right here in the middle of it. There's no hole, but the light is actually wrapping around similar to this, and it comes together, and the waves come back together here, producing a little bit of light. So the same thing happens with this, is you have all these waves like you have here, kind of similar to what you have here, but eventually they come together at this point, which is actually produces a little tiny point of light right here in the middle of this. Or you can also see like looks like these little fringes around this razor blade, and you see all these little lines going around through here. And then also you have these interference patterns, diffraction patterns, when the light passes through a small opening. Now this has to be a very small opening. And what you end up having here is you'll have some light, and then you have no light. Then you have light again, and then no light. And as you can see here with these different types of lasers, is that you'll have a bright spot, and then there's a darkness, another bright spot, a little bit of darkness. And red light, you have the same thing happening over here. So based upon the wavelength of light, you will have like different spacings in between here. But you need like various narrow openings for that to happen to a light. You need something like an opening close to about the thickness of a strand of hair, or something a little bit thinner than that. Now, interference is when two or more waves run into one another. They create an interference between the crests and the troughs. So if you have a crest and another crest, you're going to end up with a bigger crest. If you take a trough and add it to another trough, you're going to have a bigger trough. And if you have a crest and a trough, they'll basically cancel each other out. So they either partially or completely cancel each other out. And as you can see here, if you have like 2 drops of water striking at about the same time, you start getting these patterns. Or over here, there's like 2 little objects that are vibrating in the water. And if you look real carefully, it looks like there are rays coming off of this. And that is caused by interference. And if you look a little bit more carefully, you'll see basically the white areas here are the crests, the black areas are the troughs. And if you look going straight across, you'll have a trough, and right beside it you have a crest, and a trough and a crest. And they actually they'll be alternating in between one another. Now the way this works, the easiest way to look at this is just looking at 2 waves. So for example, if you have this wavelength over here, and at the same time you have this other wave at the exact same time. So this is similar to if you're playing like 2 notes on a keyboard. Or if you have 2 people singing and they're kind of singing in harmony to each other, you will start having this a little bit of interference. So just like playing 2 notes on a keyboard, you'll end up creating an entirely different type of wave. So the combination of this wave and this wave will then produce this wave right here. And the way you can look at this, you have to look at the resting point of the wave here, the thicker white line down through here. So here's the 0 point, and this wave is 2 units above. If you look at this one, this wave is 2 units below. So because of this is 2 above and 2 below, the result is 0. Now, if I go over here at this time frame, I have 2 units down, and this one is at the 0 point. So basically it's like having a -2 plus 0 will give me a -2. Or this one is 2 units up, and this one is also 2 units up, and because of that, this one is 1, 2, 3, 4 units up. And so all you're doing here is you're just basically drawing a line straight down, find out how many units is this one located, where is this one located, add those 2 together, and that is a new point from that. So this wave and this wave at the same time would then produce this wave. Now, one other thing that waves can be done to them is they can also be absorbed. So when waves are absorbed waves can be absorbed by different types of materials. So various materials will dampen or lessen, or sometimes even are able to stop the wave. So for example, like in some recording studios or something like that, you'll find these rooms where they have all these wedges on here, and that's to help absorb a lot of the waves. Give you an example of this is that if you ever gone in the gymnasium and there's just not that many people, it tends to be very loud, very echoey. But if you go into the auditorium or if you go into the band room, if you look on the walls, you'll see these slots in the walls. And those slots are to help absorb some of the sound waves. If you go into the auditorium and look straight above you, you'll find these panels that have these slots in them. And the purpose of those is to absorb the sound waves. Without that, if you were to take all those things out of the auditorium will sound very similar to what it sounds like in the gymnasium. Now, a couple other places where you'll find them, for example, basically that's like your earplugs. Or if you look at power lines, sometimes you'll see these little nodules on the lines here. And these little nodules, and from this one right here, it's actually this. Or sometimes you'll see like these kind of these triangle-shaped objects on the power lines. And when the wind blows across the power lines, this sometimes will cause the power lines to start vibrating, which is not good for them, and it causes a lot of stress. These things will help dampen out those vibrations. Or if you look at a shock absorber in a car, as a car is going over bumps, this is to help dampen out the vibrations of the wheels and prevent it from being transferred into the body of the car. Or if you look at a semi and the ones where they're carrying some sort of liquid, they have within those these baffles. And if it was just a hollow vessel, and if a semi is driving holding some sort of liquid, if they came to a if they came to a stop, the vehicle will come to a stop, but then all the liquid would rush up towards the front and will cause the vehicle to lunge forward, and which then can a lot of times can possibly cause an accident. So they put these baffles in here, and it causes a lot is to help absorb a lot of the wave action that takes place with the liquid here. This is a tower, I'm not sure which country, but it's in an area that's very prone to earthquakes. And within this, they have this ball that sits inside of here. And this is a picture of that ball. So when the event of an earthquake, as the building is rocking side to side, this ball dampens out the vibrations of the building and will help protect the building from collapsing due to an earthquake. A lot of very tall towers have some sort of dampening system of some form or another. This one has one that's actually more of a tourist attraction where you can actually see this thing and being used. And also dealing with light can also be absorbed here. And as light travels down at different depths within the water, different colors of light will be absorbed. So within a very short distance going down to the water, more of your reds and your deep blues will begin to be absorbed. And as you go a little bit further down, more of your oranges and some of your purples. And the ones that are able to penetrate furthest into the water are mostly your blues and greens. And that's one reason why if you ever look into look straight down into a very deep portion of the water, everything tends to be kind of a bluish green color. And it's because all the other colors have been absorbed here. So for example, here's a photograph, two photographs of the same thing here. So if you look at the seahorse and this coral, without any aid, this is what the seahorse would look like, kind of a grayish color. But if you use like a flash photograph and actually introduce a little bit more white light to it, this seahorse is actually more of an orangish red color. And then also same thing with the coral. There's a little bit of red and pinks in the coral here, but without this, it looks like it's more of almost like a grayish color to it. And this is actually came from a video of a scuba diver where he had these colored tubes, and as he dove down, you can see how the colors have basically been kind of muted out and how much they have changed from basically close to the surface to about over 90 feet into the water. So a lot of the colors have been absorbed as you go further down. So again, various wavelengths of light are absorbed at different depths in water. And again, you can get a closer image or a closer look of the image of the seahorse. So without any additional light added to it, everything kind of looks more of a bluish green color to it. But in actuality, this is what the seahorse and the coral actually looks like. And also waves can be scattered. And scattering is either reflected or refracted light that are moving in multiple, basically random directions. So for example, if you shine a beam of light at a brick wall, some of the light is going to be reflected coming off of that, and so anyone from any direction is still able to see it because the light is going on all different directions. So someone standing over here will see a little bit of light. Someone standing over here will receive a little bit of the light. And it's because the light is scattering in many different directions. Or if they have light that's being refracted as it passes through it, because of the irregular surfaces of the material, as the light strikes it, some of the light will go one way, some of the light will go a different way. And as you can see, like in this frosted glass, as the image is passing through the glass here, you don't get a very refined image of who's behind the glass. Now, later on, we'll get into some additional information about waves here. We'll get into just like one more section of the notes here. But for now, there are some questions.